Hello everyone, welcome to Module 1 where I will be explaining theoretical yield and percentage yield as well as some of its real-life applications, and we'll be going over some examples. So let's dive straight into this and go over the main focus today, which is what even is percentage yield. So percent yield is a measure of the quantity of the moles of a product in comparison to the reaction consumed. It is a very important measure of the efficiency of the chemical reaction technique, and this is very critical in the synthesis of organic compounds. The formula derived for the percentage yield is the actual yield over the theoretical yield multiplied by 100%. Chemical reactions in the real world don't always go exactly as planned on paper. In the course of an experiment, many things will contribute to the formation of less or more product than what would be predicted. Besides spills and other experimental errors, there usually are losses due to an incomplete reaction, undesirable side reactions, etc., which we will get more into later. Chemists need a measure that indicates how successful a reaction has been, and this is what is called percentage yield. Before we move any forward, we need to break down the components of the percentage yield and define what the theoretical yield is. As you can probably guess by the meaning of the word theoretical, the theoretical yield is the yield that chemists estimate on paper from a given calculation, and this is done using stoichiometry. In other words, it is the calculated quantity of a product expected in given quantities of reactants. It is the maximum amount of product that can be formed from given amounts of reactants. On paper, it is assumed that every molecule of reactant converts flawlessly into a product. When two substances react, it is impossible to have them present in the same amount for both of them to react completely. One of the reactants will always run out before the other one of the reactants. So if we look at this example over here, reactants A and B create product C, and we can see evidently that the reactants are not consumed at the same rate. So the reactant that runs out first and is completely consumed in the reaction is defined as the limiting reagent. It limits the total amount of product that is formulated. Once the limiting reactant is entirely consumed, no more products will form, and the reaction will stop. Even though one may assume that the reactant with a smaller initial quantity will be the limiting reagent, we will find out later in this lecture that that is not always the case. When determining the limiting reagent on paper, the only way that this can be done properly is by using stoichiometry. By looking at our example from before, we can see that reactant B is completely consumed when product C is formed. So this will be our limiting reagent. The other remaining reagents that are not completely consumed when the reaction stops are known as the excess reagents. In other words, this is anything that is left over. On paper, we don't really care about the excess reagents when it comes to determining the theoretical yield. Obviously, it still needs to be identified so that it can be distinguished from the limiting reagent. However, the excess reagent will not be used to determine the theoretical yield, as not all of the reagent goes towards making the final product. In our example from earlier, reactant A is still evident, even after the reaction has stopped. Even though some of reactant A went towards formulating product C, we can see that this cannot be used in the calculations because a good portion of reactant A still remains as a reactant, which means that reactant A is the excess reagent. In order to grasp an even better understanding of this crucial topic, let's compare chemistry to cooking. To make a sandwich, you will need 2 slices of bread and 1 slice of salami, and that will make 1 sandwich. Now, you want to determine how many sandwiches can be made with 7 slices of salami and 10 pieces of bread. Some may assume that the salami will be the limiting reagent because its initial quantity is less. However, we can see that 7 salami will make 7 sandwiches and 10 bread will make 5 sandwiches. The bread will be consumed first, leaving excess salami, and this makes bread the limiting reagent. Looking back at our percentage yield equation, we need to define its other crucial component, the actual yield. The actual yield is the quantity of product that is actually produced. This is the yield number that is derived from actual experiments that are performed in a laboratory setting. This is different from the theoretical yield, as a theoretical yield is determined from a paper calculation. There are three different cases for what your percentage yield outcome means. The first case is that the actual yield is equivalent to the theoretical yield. The percentage yield will equal exactly 100%. This is very, very, very uncommon, as systematic errors and random errors are almost always bound to happen. The next case is when the actual yield is greater than the theoretical yield, resulting in a percentage yield that is greater than 100%. This is a result from an error in technique, as you cannot get something from nothing. Some products are formed as a precipitate from a solvent. If the product is weighed when it is wet with solvent, the results will be a larger than expected mass. A more thorough drawing of the product will give a more accurate yield determination. Another possibility is that the product is contaminated with an excess reactant or a byproduct, which makes the mass of the product appear larger than expected. A product must be purified before its yield is determined. The last case is when the theoretical yield is greater than the actual yield, resulting in a percentage yield that is less than 100%. There are a few factors which could result in reduced actual yield. The first reason is that the product of the reaction rarely appears in a pure form. Some products may be lost during the necessary purification steps, which reduce the yield. The second reason is that the reactants may participate in reactions other than the one of central interest. These are called side reactions, which produces unintended products called byproducts. The yield of the main product is reduced by the extent of the side reaction occurring. The final reason is the possibility of a reverse reaction occurring, where some of the expected products may react to reform the reactants, resulting in the yield being less than expected. Now let's try an example. Here we have a cellular respiration reaction occurring where glucose and oxygen are converted to carbon dioxide, water, as well as energy. We are asked to find the mass of carbon dioxide that will form with 27 grams of glucose and 43 grams of oxygen. The first step to solving this is to balance the equation. When looking at the question, we can see that it is clearly not balanced. By adding a 6 in front of the oxygen, a 6 in front of the carbon dioxide, and a 6 in front of the water, we can now see that we have 6 carbons, 12 hydrogens, and 18 oxygen on each side. The equation is now balanced. The second step is to convert our given masses into moles. We can't really do anything with the mass, so converting it into a mole is crucial in order to go on with the experiment. Using our formula of moles equals mass over mole mass, we can substitute the values in for each compound. The molar mass can be found using the elements on the periodic table and multiplied by how much of each element is present in the compound. The third step is to calculate the moles of product that each reactant has the potential to make. This is how we will determine our limiting reagent. To do this, we will multiply the moles of each reactant that we calculated in the previous step over the coefficient of the product over the coefficient of the reactant, which can be found from our balanced chemical equation. And this is called the molar ratio. We can clearly see that glucose creates less product than oxygen. So glucose will be the limiting reagent, and oxygen will come in excess, hence its larger number. The number of moles of carbon dioxide that can be produced from glucose will be the number used in figuring out the mass. The final step is to go back to the mole formula and rearrange it to find the mass. We multiply the moles of carbon dioxide, which we just calculated in the previous step, by the molar mass of carbon dioxide, which can be found using the periodic table, to obtain a mass of 39.6 grams, which will be rounded to 40 grams to maintain the two significant figures. The next question is asking us to find the percentage yield when the mass is 34.8 grams, which was found in a laboratory experiment. The mass calculated in the laboratory experiment is the actual yield. And the work that we did before to find the yield of carbon dioxide on paper, when it is assumed the reactants convert flawlessly to products, is the theoretical yield. Going back to our percentage yield formula, we plug in the values that we know and multiply by 100%. In terms of the theoretical yield, we'll use our answer with three significant figures instead of two to obtain a more accurate response, and we will find that the percentage yield is 87.9%. Calculating percentage yields is used in many corporations in order to maximize revenue when manufacturing products. When developing drugs, pharmaceutical companies want to attain the highest percentage yield in order to save money. Copious amounts of time and money are spent improving the percentage yield for chemical products. When complex chemicals are synthesized by many different reactions, one step with a low percent yield can quickly cause a large waste of reactants and unnecessary expense. Thank you so much for listening to my presentation. I hope that you learned something new about theoretical yields and percentage yields, and I hope that you can apply this outside of your studies.